We are in section F of chapter 21, and we're talking about points of inflection and how they affect the shape of a curve. So let's talk about what a point of inflection actually is. It has to be a point, first of all. The function has to exist there. The second qualifier is that the second derivative at that point would have to equal 0, and the second derivative would actually have to change sign there. Okay, so that's your basic definition of what a point of inflection is. So let's first of all talk about what the second derivative tells us. It tells us what's called the concavity of the curve over a certain area. If the second derivative is greater than 0 for some part of the domain of the function, then what's happening is I'm having a slope, but the slopes, as I move from left to right, the slopes are increasing, which means that if they're negative, they're getting less and less negative, and if they're positive, they're getting more and more positive. So let's say I'm starting off with a slope of -5, and I allow my slopes to get less and less negative. That means they're increasing. So maybe to -3, and then -2, and then -1, and then a slope of 0 eventually. And then once I get past a slope of 0, if I still want to increase the slopes, well, now the slopes are becoming positive. Not very positive, but positive. And then they're getting more and more positive and more positive. Okay? And if I do that, that looks like a smiley face. So I basically say if the second derivative is greater than 0, that's called concave up, meaning that the curve opens upward and it looks like a smiley face. All right. And then conversely, if I have the second derivative less than 0, that means that my slopes are decreasing. So let's say I'm starting off with a very large positive slope, and then I want my slopes to become less positive, less positive, less positive, until I get to a slope of 0, at which point my slopes will keep decreasing, meaning my slopes will get more and more negative, and more and more negative, and more and more negative. Alright, so that would be concave down because the curve opens down and it looks like a frowny face. So that's the two things. If the second derivative is positive, then the original curve is concave up, and if the second derivative is less than 0, then the original curve is concave down. All right. Now, there are two types of inflection points. An inflection point then basically is where does it change from being a smiley face to a frowny face, or vice versa? When does it change from a frowny face function to a smiley face function? And there's two ways that can happen. It can happen at a stationary point, which we've already talked about as a point where the first derivative is equal to 0. So if I look at a graph that looks like this, all right, now I can see that everywhere to the left of this point there is a frowny face type function. It's the left half of a frowny face function. And then to the right of this point, it is the right half of a happy face or a smiley face function. So this is a point of inflection, but not only that, because the slope of the tangent line at that point is 0, then it is a horizontal or a stationary inflection point. The only other thing that can happen with inflection points is that the inflection point does not have a horizontal tangent line, and that could look something like this. Alright, so where does it change from frowny face to happy face? Right about there. And if I look at the slope of the tangent line there, that is not horizontal. Okay, so that would be a non-horizontal or a non-stationary inflection point. So look at the first derivative of your inflection point to see whether it is horizontal or stationary. Either one of those means the same thing, or non-horizontal or non-stationary. Okay, and both of those mean the same. So let's do an example. We have f of x equals 3x to the fourth minus 16x cubed plus 24x squared minus 9. We're going to find and classify all the points where f prime equals 0. Then we're going to find and classify all of the points of inflection. And then we're going to figure out where it's increasing and decreasing, and we're going to figure out where it's concave up and concave down. Two separate questions. And these two parts go together, and these two parts go together. So let's find where f prime of x equals 0. There's the first derivative. 12x cubed minus 48x squared plus 48x. If I factor that, I get 12x times x minus 2 all squared. So there are two x's where the first derivative is 0, x equals 0 and x equals 2. So here's what I'm going to do. Here are the 2 points where the first derivative is equal to 0. I am going to pick a number that is less than 0 and see what happens to the first derivative. So if I pick -1, well, 12 times -1 will be negative, and -1 minus 2 will be negative, but when I square it, it will be positive. So the first derivative is negative everywhere before x equals 0, which means that my original function is decreasing. Then if I move between 0 and 2, try a number like 1, 12 times 1 will be positive, and this whole squared thing will still be positive, so positive. Meaning that the original function is increasing. Alright. Then I look at points that are greater than x equals 2. So let's try 3. 12 times 3 will still be positive, and 12 minus 2 squared will still be positive, so this is still positive. The original function is still increasing. So what's going on here? If I have a function that is decreasing and then increasing, then what's happening here is I actually have a minimum. Okay? But if the function is increasing before this point and then still increasing after, it looks like that is going to be a point of inflection. Okay? So those are all the points where f prime is equal to 0. Now let's look at the points of inflection. Well, I'm going to set the second derivative equal to 0. And there's my second derivative, 36x squared minus 96x plus 48. And if I factor that, I get 12 times x minus 2 times 3x minus 2. Set that equal to 0, and I get x values of 2/3 and 2. So let's look at my number line again. I've got 2/3 here, and I've got 2 here. So let's look at what's going on everywhere else. Before I get to 2/3, let's try x equals 0. At x equals 0, 12 is positive. X minus 2, 0 minus 2, that's negative. And 3 times 0 minus 2, that's also negative. So the second derivative is positive, meaning that the original function is concave up. Alright, and then if I try a number between 2/3 and 2, let's try x equals 1. 1 minus 2 will still be negative, but 3 times 1 minus 2 will become positive. So the whole thing is negative, meaning that between 2/3 and 2, the function is concave down. Alright, then after 2, I'll try a number like 3. 12 is still positive, 3 minus 2 is now positive, and 3 times 3 minus 2 is still positive, so this is positive, and that means that the original function is concave up. Okay? So, since I do have a point of inflection here, because the second derivative actually changed sign. Okay? Just because the second derivative is 0 doesn't mean it's a point of inflection. It has to actually change sign before and after that point. Alright, so these are both points of inflection because the sign changed from positive to negative here and from negative to positive here. The sign of the second derivative changed. Now let's figure out whether they are stationary points of inflection or non-stationary points of inflection. Well, at x equals 2/3, this function does not have a slope of 0 because I didn't have 2/3 as one of my points on this line where the first derivative was equal to 0. So the first derivative is not equal to 0 here. So that means it is a non-stationary point of inflection. But if you look at x equals 2, it was listed here as one of those points where the first derivative equals 0. So there's a horizontal tangent there, and it's a point of inflection. So this is a stationary or horizontal point of inflection. All right, and we will be doing more examples like this in class. Please email me any questions you have between now and then.